There's a company you've almost certainly never heard of. It doesn't make phones. It doesn't make cars. It doesn't run social media or sell you anything. But right now, at this exact moment, virtually everything you use that runs on electricity exists because this company's machines made it possible. Their headquarters sits in Veldhoven, population 44,000. It's a quiet Dutch town in the province of Brabant, surrounded by farmland, an hour south of Amsterdam. There are no flashy storefronts, no Apple Park-style campus with curved glass and infinity pools, just a series of industrial buildings growing so fast the company has bought up surrounding streets, demolished houses, and is eating the town alive. The company is ASML, and it may be the single most strategically important corporation on the planet. 90% of all computer chips manufactured today are made using ASML's machines. Not some of the chips, 90%. The processors in your phone, your laptop, your car's braking system, the satellites tracking weather patterns, the missiles hunting targets, the supercomputers trying to cure cancer, all of them pass through equipment built in this one Dutch town. When the COVID pandemic hit and the world ran out of chips, it wasn't because chip makers failed. It was because the machines that make chips can't be built fast enough. There is no backup supplier. There is no plan B. There is only Veldhoven. And now, two superpowers are at war over who gets to use it. This is the story of how a failed Philips spin-off became the most consequential industrial company in the world, and what happens when geopolitics comes for the one thing keeping modern civilization running. In March 1984, a Dutch electronics giant called Philips couldn't figure out what to do with a machine nobody wanted. Philips had spent over a decade developing a device called the silicon repeater, essentially a super-precise projector that could etch circuit patterns onto silicon wafers. The physics were extraordinary. The commercial interest was zero. The chip manufacturers they showed it to weren't impressed. Internal managers thought it was a money pit. Even the engineers working on it weren't sure it had a future. So Philips made a deal. They'd combine the technology with a small chip machine company called ASM International, owned by a pioneering Dutch entrepreneur named Arthur Del Prado. Together they'd form a joint venture. They'd give it 50 ownership. They'd give it a modest budget. And they'd give it a deeply unsexy name, ASM Lithography, later shortened to ASML. 40 people, a drafty factory floor, and a machine that no serious chip manufacturer had yet agreed to buy. The first CEO, a glider pilot named Jalt Smit, flew to Silicon Valley in 1984 and got dismissed on the spot. The message was direct. Come back when you've sold 50 machines. No one in the market thought ASML had a chance. They were too small, too new, and the competition, American giants like GCA and Japanese powerhouses like Nikon and Canon, had decades of experience and loyal customers. But Smit saw something the others missed. The industry was about to hit a wall. Existing machines couldn't produce chips small enough for the next generation of computing. ASML had the technology to break through that wall. All they had to do was not die long enough to prove it. That turned out to be harder than it sounds. Through the late 1980s, ASML lived on government subsidies, Philips' goodwill, and pure stubbornness. They nearly went bankrupt twice. Their joint venture partner couldn't keep up with capital calls and eventually walked away. What saved them, in the end, was Taiwan. In 1987, a Taiwanese-American engineer named Morris Chang was handed an unusual mandate: build a national semiconductor industry from scratch. He needed an experienced partner. He approached the big names: Intel, Texas Instruments. They said no. So he went to Philips, which agreed to take a stake, and opened the door to ASML. Chang's company would be called TSMC. You probably know what it became. ASML gave TSMC their first machine for free. If it worked, they'd pay. The Taiwanese were skeptical, but willing. And it worked. ASML had their first marquee customer. TSMC had the foundation of a chip empire. The two companies would spend the next 3 decades building each other up into something the world had never seen. By the mid-1990s, ASML had cracked the secret of staying ahead. While Nikon and Canon obsessed over perfecting each machine before shipping, ASML shipped first. The machine would arrive, still technically unfinished, and engineers from both companies would work together in the fab to fine-tune it in real conditions. It was chaotic. It was sometimes infuriating for customers. But it was faster. And in the chip industry, faster is everything. They went public in 1995. Their stock has increased roughly 600-fold since then. By 2001, they'd absorbed America's last lithography company, SVG, bringing with it the licensing rights to a technology so strange, so difficult, and so crucial that it would define the next 2 decades of industrial history. That technology was EUV, extreme ultraviolet light, and chasing it would almost destroy them. To understand what ASML was attempting, you have to understand Moore's Law. In 1965, an Intel co-founder named Gordon Moore noticed something. Every 2 years or so, engineers managed to double the number of transistors, the tiny switches that process information, on a given chip. More transistors meant more speed, more efficiency, more power. The law became a self-fulfilling prophecy. The whole industry organized itself around hitting that doubling target, almost like clockwork. But physics has opinions. By the early 2000s, it was clear the existing technology, deep ultraviolet light, was approaching its limits. To keep Moore's Law alive, the industry needed to print circuit lines at a scale so fine that conventional light simply couldn't focus tightly enough to draw them. The answer, in theory, was light with a much shorter wavelength. Extreme ultraviolet light at 13.5 nanometers would do the job. The problem? EUV light is so energetic, it's absorbed by nearly everything, including air. You can't bounce it off a lens. You need mirrors. You need a perfect vacuum. And to generate EUV in the first place, you need to shoot a laser at a droplet of molten tin, 50,000 times per second, to create a plasma hotter than the surface of the sun. You then need to catch the light that plasma emits with a precisely curved mirror and aim it at a silicon wafer with an accuracy of 1 nanometer, about the distance your fingernail grows in 1 second. ASML committed to this in the late 1990s. They signed their first commercial deal for an EUV machine in 2006. That machine was supposed to be delivered by 2010. The first working EUV chips didn't roll off a production line until 2019. In between, 20 years of near-miss breakthroughs, humiliating public failures, billions of euros burned with nothing to show, and a single Australian engineer in a San Diego lab who spent years firing lasers at tin droplets and watching everything go wrong. The light source was the core problem. ASML was working with a company called Kymer to develop it. The principle was clear. The execution was a nightmare. Reflected laser light kept destroying the laser itself. The mirrors kept getting contaminated by tin splatters. The power output was nowhere near what chip manufacturers needed. There were moments when even Martin van den Brink, the brilliant, terrifying technical director who was the beating heart of the whole project, quietly wondered if they'd made a catastrophic mistake. To save EUV, ASML pulled off one of the boldest financial maneuvers in tech history. In 2012, they sold stakes in themselves to their 3 biggest customers. Intel, Samsung, and TSMC each bought in. The cash funded the acquisition of Cymer, which gave ASML direct control over the light source. The message was clear. If EUV succeeds, we all win. If it fails, we all lose together. And then, in early 2018, an engineer noticed something odd. The contaminated mirrors were mysteriously cleaning themselves during maintenance. A chemist figured out why. Oxygen. A tiny puff of oxygen injected into the vacuum kept the mirrors clean. One pipe. One chemical insight. 20 years of struggle. Solved. ASML called Samsung, told them to come to Veldhoven. The machine was ready. In his 2023 State of the Union address, Joe Biden spent the first 10 minutes talking about chips. Not abstract geopolitics. Not AI. Chips. Their absence from American cars and refrigerators. The fact that the U.S. once made 40% of the world's chips and now makes just 12%. The fact that a pandemic had exposed how completely the entire Western economy depended on factories in Taiwan. One island, 100 miles off the coast of mainland China. Biden understood what ASML represented. So did Xi Jinping. So did every serious defense analyst on the planet. The machines in Veldhoven don't just make consumer electronics. They make the chips that guide missiles, run satellite surveillance, power artificial intelligence, and process the data that decides who wins the next war. Control the chip, and you control the future. China had been buying ASML's machines for years, hundreds of them. SMIC, China's largest foundry, had signed a contract for ASML's most advanced EUV systems. Everything was legal. Everything was proceeding normally. Then the Trump administration decided it wasn't. Starting in 2018, a quiet but relentless American diplomatic campaign was aimed at The Hague. The U.S. wanted the Netherlands to deny ASML an export license for EUV machines destined for China. The argument was national security. Advanced chips could be used for military AI, cyber weapons, hypersonic missiles. The U.S. couldn't let China close the gap. The Dutch were caught. ASML's Chinese business was enormous and growing. China represented a massive future market. The Netherlands had historically stayed out of chip politics and let companies trade freely. But America was its most important strategic ally, and the pressure was personal, direct, and escalating. By late 2019, the license was quietly denied. No EUV machine would go to China. But that wasn't enough for Washington. By October 2022, Biden's National Security Council had spent months in secret trilateral negotiations with the Netherlands and Japan, hammering out rules to block not just EUV, but ASML's older conventional deep ultraviolet systems as well. The Chinese had been using those machines combined with clever multi-exposure tricks to approximate the results of EUV without actually having it. The U.S. wanted to close that workaround too. The deal was done in early 2023, right after Mark Rutte's invitation to the White House. Biden called ASML "our companies" by accident in front of the cameras. The Dutch could see exactly where this was headed. What followed was a rolling series of export restrictions, license revocations, and blacklists. ASML found itself revoking approved export licenses it had already issued, telling Chinese customers their machines were ready, packaged, waiting on the dock, but couldn't ship. Following orders from Washington that arrived faster than Dutch law could formally process them. And here's the brutal irony the Veldhoven engineers can't stop thinking about. Every time ASML is locked out of China, Chinese companies like ASML, the state-backed lithography manufacturer in Shanghai, get a little more desperate and a little more resourced. There are no legitimate customers for a Chinese-made machine until foreign machines are banned. The export restrictions are building the very competitor they're trying to prevent. Peter Wenink, ASML's outgoing CEO, put it directly to an American senator who had spent 10 minutes warning about China's dangers. You don't know all the facts. The senator did not enjoy that. There's a moment near the end of this book that I keep coming back to. It's 2006. A project leader named Hans Mehling is staring at the first wafer ever exposed by ASML's prototype EUV machine. He's looking at the image, the product of decades of theoretical physics, billions of euros, thousands of engineers, international collaborations, multiple near bankruptcies, and an entire industry holding its breath. The image looks like bananas, fuzzy, blurry, semicircular shapes that sort of vaguely resemble bananas. That's it. That's the great EUV breakthrough, a banana. From that banana to the iPhone in your pocket was 13 more years of work. 13 years of cleaning contaminated mirrors, solving reflected lasers, managing the paranoia of chip manufacturers who had been promised the impossible, managing the politics of 3 competing governments, managing a workforce of 42,000 people in 16 countries, all organized around the obsessive, confrontational, brilliant, clumsy, paranoid vision of one Dutch physicist who used to disassemble his mother's appliances as a child just to understand how they worked. What ASML built isn't just a machine. It's a proof of concept for a particular kind of industrial civilization. One where deep collaboration across dozens of companies, universities, and countries, German lens makers, Dutch engineers, Taiwanese chip foundries, American laser manufacturers, Belgian research institutes, can produce outcomes that no single actor could ever achieve alone. That model is now under threat, not because the technology failed, because politics caught up to it. The tech war isn't just about chips. It's about whether the interdependent global economy that made ASML possible can survive the return of great power competition. Whether a world that needs free trade to function can coexist with national security imperatives that demand walls. Marc Hijink spent a decade embedded in ASML to write this book. What he found wasn't a triumphant corporate story. It was something more complicated. A genuinely extraordinary organization, built by genuinely extraordinary people, suddenly thrust into a confrontation for which nothing in their history had prepared them. They built the most complex machine on Earth. They did it by ignoring politics for 40 years. Now the politics won't let them be ignored. For the first time, ASML doesn't control its own future, and neither does the world it made. Focus. The ASML Way, by Marc Hijink, is essential reading if you care about technology, geopolitics, or what the next 20 years of the global economy actually look like. Not because it has easy answers, because it shows, in extraordinary detail, just how fragile the whole thing was, and how fragile it remains. That's everything. See you next time.